Okay, good afternoon, everyone. Welcome to the February edition of the VLab Forum. A reminder that the presentation is recorded, and John Chattel, who administers the VLab Forum, will upload the recording to the website shortly after the forum's concluded. Today's speaker is Trevor. Another reminder is to mute your locally if you're are we? Hang on a second. Stand by.
I think I may have muted the right person.
Okay. So our today's speaker is Trevor Alcott. Trevor presented this talk at the annual NCEP review back in December, and there was quite a bit of discussion, a lot of interest in this, so we thought we'd invite him here to essentially try to hit a larger audience, or folks who weren't able to participate in that. It's very focused on the same sort of R2O, O2R things that we're looking at in weather service. NCEP is providing ensembles. They're focused on improving models. The question then becomes is how do our operational offices apply the ensemble output in ways that can improve the services and products that we deliver to the public. So Trevor's made a really good cut at I think at trying to tackle this type of a problem, and there's been subsequent discussions about this, and they'll continue, I'm sure. So without further ado, I think we'll hand over the mic and the presentation to Trevor. And a reminder, our format's about 30 minutes or so of presentation with the remainder of the hour for question and answer. So please, if you have questions, send them in to us either through the chat feature or use the raise your hand feature and we'll unmute you during the Q&A period so that you can ask it over the phone. Trevor, you there?
I'm there.
Okay, and you're on. Go ahead.
Great, thanks, John, and good afternoon, everyone. Today I'm going to be focusing on the Ensemble situational awareness table we've developed in Western Region, and also making more general comments really about how we're trying to take better advantage of Ensemble data and try and move the field forward, especially in the West. And I want to start off by acknowledging contributors, Rainey Graham and Nanette Ozenfeld at the WFO in Salt Lake, Chad Kaler in my group in Western Region, and Rich Grum at WFO State College. So one of the things that we really try to do in my group in Scientific Services Division in Western Region is we want to move the DSS effort forward. And there's a critical issue with DSS where if we get really good at communicating mediocre information, we really haven't solved the problem. So we're trying to use good science and make that information about what's significant, about forecast confidence and what the potential impacts are. We want to make that information better using the best science we can. Part of that is visualization tools, but another big component is verification, something I like to call better living through verification. So there's all this guidance out there, and especially in the case of ensemble output, we don't always know what it's good at and what it isn't. So a lot of forecasters are asking the question, should I believe it? Should I believe what I see, especially in the ensembles? So the first thing I'd like to get at is the significant side of things. So we want to put the forecast in a climatological perspective. Now there's a couple ways to accomplish this. The first one, and most commonly used, being an R climate. So this is a reanalysis climate. How does the model forecast compare to typical conditions at this time of year? So for example, you don't usually get a trough this deep in September. We want a forecaster to easily be able to say that by looking at a simple situational awareness tool. Now, a second technique that hasn't been used a lot, but it's just starting to gain traction, is called M climate. so making comparisons to the model climate. So how does the model forecast compare to what is typically forecast at the same lead time this time of year? So you might say something like, well, the model rarely shows precipitable water this high 5 days out. Or even more commonly used in case of precipitation, the model rarely shows this much QPF at a 5-6 day lead time. So just focusing on the our climate side of things, how are we calculating that? Well, first off, we want to quickly identify where and when the forecast departs from climatology. And we're going to take the NACE ensemble mean and compare it to a 30-year climatology of the Climate Forecast System Reanalysis, the CFSR. Now, there's somewhat of a resolution difference here, but that's going to go away, I believe, a year or two down the road with an upgraded NACE. We're trying to get kind of an apples-to-apples comparison as close as we can between the NACE and the CFSR for a 21-day window centered on the valid time. And we're accounting for diurnal effects by saying, well, we're only going to compare 0Z valid forecasts to 0Z analyses. Now, seeing this all take shape, I'm going to take you through the situational awareness tool that we've created here. And on the left, you have a table with forecast hour increasing as you go down, and going across, you have all the various fields from the NACE. So you have geopotential height, temperature, winds, sea level pressure, specific humidity, precipitable water, and also integrated water vapor transport, just a vertically integrated moisture flux. All these numbers in the table are for the given domain, what is the largest departure between the NACE ensemble mean forecast and climatology? And this is in terms of standardized anomalies. So anywhere you have a large number here, positive or negative, you have a major departure between the forecast and climatology. So what you're seeing in the NACE is a big deal. Now, just highlighting one particular image here, what I've plotted up is the 132-hour forecast integrated water vapor transport. So it's just highlighting a large area over Alaska, major event last October, of highly above normal integrated water vapor transport. Basically translates to elevated potential for a major precipitation event in that region. Now, we're very close to having this website opened up to the public. At the moment, it's just NOAA. We're just doing some formatting, but anybody with anybody on a NOAA computer will be able to access, at least for now, this website listed on the bottom. And again, we're trying to get that completely opened up to everyone. Now, when we originally did this, we were only looking at standardized anomalies. And there's a big assumption there that all the fields we're looking at are normally distributed. That's not really the case. And a good case in point here is precipitable water, say for January in Salt Lake City. You actually have a decent tail into fairly high amounts. So if you assume that a -2 standard deviation and a +2 standard deviation anomaly are just as likely, that's not the case. In fact, a -2 anomaly is completely outside the observed climatology, but +2 anomaly is fairly common, something you can get, say, 1 day a month. So to get at that, we're also plotting up percentiles and return intervals. So we can say, okay, where exactly does this forecast fall with respect to the climatological distribution? Now, just showing an example here, integrated water vapor transport is a great case here because it's not that unusual to get 6, 8, 10 standard deviations above normal, just because it's a highly non-normal distribution. It's a very long tail into high amounts. But if we were to look at percentile, you could very clearly say, okay, we have a large area of eastern Alaska and into the Yukon where your forecast IVT is outside the climate for this time of year. So it's really unusual to get this much bulk moisture transport into Alaska in late October. And right away you can say that for any area that's in cyan. We also flip this around into a return interval. And I want to say I have adjusted the wording here a little bit. I think never is a bit misleading. All we're saying is that anywhere in this bright red color is completely outside the climate for this time of year. Whereas, say, 1 day every 5 years means that around this time of year, this 18th October to 8th of November, you could expect to see 1 day every 5 years, late October, where you get amounts that high. So it's a bit of a mouthful, and that's why I try to get people to focus just on when are we completely outside the reanalysis climate for this time of year. That really helps narrow down what's a big deal and what isn't. I just want to briefly touch on model climate, and I think this is particularly relevant for QPF. In this case, we're comparing a GEFS mean forecast QPF to the GEFS reforecast climatology. This is just a sample graphic. We don't have this worked into the table yet, but just to show how this might be useful, this was a case for a major blizzard in Wyoming and the Dakotas back in early October, where you could look at the GEFS mean QPF and really not get excited. And in fact, a lot of the upper level fields didn't look that impressive. But once you compare that to a climatology, you can see that it's actually really unusual to get this much QPF in the ensemble mean at a 4-day lead time. So right away, that would jump out at you. So talking more about the ensemble mean. So we're trying to use the ensemble mean as a confidence tool. And it relies on this idea that for a multi-model ensemble mean to depart from climatology, you need most of the members to show a significant feature in the same location at the same time. Now, the hypothesis there is, well, if we are using this multi-model ensemble mean, we don't have a lot of under-dispersion issues, especially at medium to long ranges. It probably misses a lot of extreme events, but when it does go big, it's usually right. And we're going to look at some verification that makes a pretty good argument that that's true. So first of all, just digging into using this as a confidence tool, well, if you looked at a sample spaghetti plot on the left, say this is 500 millibar heights, if your ensemble members aren't really showing a significant feature and there's a lot of disagreement among them, your ensemble mean is probably going to look a lot like climatology. So looking on the right, just really small departure there. Whereas if you start to get a couple of members that are showing maybe a significant trough digging in the desert southwest, you do get a small departure here. But again, there isn't enough agreement in the ensemble to really get a big departure from climatology. Same is true if you have some significant feature, but the members don't have it in the same place. But in the final case here, if you can get all or at least a majority of the members of an ensemble to show a significant feature, again, same place, same time, you'll get a large departure between the ensemble mean and climatological values. So what does that mean? Well, it means that if you can look at a comparison between the ensemble mean and climatology, major features at long ranges really stand out. So it's really hard to get, say, a major trough to show up in the ensemble mean at a 10-day lead time. But when it does, should we really be paying attention? And this is where I've got some verification that lends some good support. Now, this is a busy plot, but I'd like you to focus on the bottom right-hand plot. Now, this is verification over last January to last October of the 10-day NAIFS ensemble mean forecast 500 heights. So you've got the forecast anomaly on the x-axis, analyzed anomaly on the y. And your solid green line here is the average of how those verified. Your 10th and 90th percentile of how they verified are in the dashed lines. So we focus on this red dot. What that's telling you is that when a NAIFS ensemble mean forecast, day 10, was a +1 standard deviation anomaly. So when there was basically a significant ridge forecast, 90% of the time, heights at least verified above normal. So what this is saying is at a long lead time of 10 days, there's some useful information in the NAIFS. if it's picking up on a significant departure from climatology, it's worth paying attention because it's probably going to verify. If you look at shorter lead times, say in the bottom left, those are fairly good forecasts at day 6, where if you do see, again, a significant departure, it's likely to verify as a significant ridge, significant trough. So there's good forecast information there about the overall pattern at much longer lead times than we may be used to. Well, when you look at other fields such as moisture, showing precipitable water anomaly verification here, yeah, there's obviously a degradation in skill. I think you could argue we're probably 10 to 20 years in skill lagging behind the overall pattern when we try and forecast moisture. And that really comes out here, but look at the day 6 verification in the bottom left, and when you do get these +2, +3 standard deviation forecasts, again, they tend to verify at least +1, +2 anomalies. So this is a case where if you're in the desert Southwest and you're trying to pick up on a significant monsoon surge, you're finding some useful information in the multi-model NACE ensemble mean. So again, you see a large departure from climatology, big-time moisture surge, it's likely to verify somewhere in the ballpark. So you can pick up on a significant moisture surge at day 6. Similar signal for wind speed. I'm basically making the same point here, so I won't belabor it too much, but I would like you to look again at the 6-day verification. You can see when there's a forecast of 50 knots at 700 millibars, 90% of the time it's verifying at least 40 knots. So in the case of picking up on significant wind events, we're starting to do that out at a fairly long lead time. The thing I do want to clarify, all these plots have been shown for the entire North American domain. If you run them on smaller domains, you don't see a big difference. You just end up with a smaller sample size. The statistics aren't as great. But the overall message is really the same, and the predictability limits are quite similar if I were to look at this for, say, West Coast, East Coast, or full CONUS. So taking this a step further, what about probabilistic forecasts? So if we looked at what fraction of the NACE members produce something really unusual, in this case I'm saying, well, what fraction produce an extreme forecast? Now, I have to be careful here because I'm using extreme loosely. So all we're saying is it's outside the 3-week climatology. So think back to those large, bright red areas where we're forecasting something that's completely outside the climatological PDF. So these aren't necessarily, and in fact, they're rarely all-time highs or lows. But you have a good balance here because with 3 weeks, you're looking at events that are common enough that we can evaluate forecast skill, but they're still rare enough that they're associated with impacts most of the time. So I think this 3-week window it actually works out quite well for us. Just showing an example of that. One of the options in the table is that you can pull up NACE probabilities. And for a smaller subset of the fields, you're going to have a table here that's showing, okay, what's the maximum percentage of the members that show an extreme event, that show something outside the climatological PDF. In this example here, you have an area over kind of the southern Gulf of Alaska where greater than 90% of the members have temperatures warmer than anything in the climate for this time of year. And that, excuse me, that's out at a fairly long lead time of 144 hours. So the question is, are those probabilities reliable? So once again, better living through verification, we ran the numbers for last January through late October. And you'll find that these forecasts, at least for unusual 500 millibar heights, they're fairly reliable. And they're fairly reliable at lead times of up to 7 days. It tends to drop off in the 10-day range. And you'll notice that both for extreme max forecasts, so just exceptionally strong ridges on the left and exceptionally deep troughs on the right, kind of focusing on these bottom 2 plots. So again, good reliability of probabilistic forecasts coming out of the NACE. Similar thing, just showing another example for 700 millbar wind speeds. Again, these are fairly reliable forecasts. You'll notice that some of these lines are fairly short for 5, 7, 10-day lead times, just because you don't get a lot of cases of high probabilities of something really unusual at a long lead time. You just can't get enough of the members to agree on the same really significant event at the same time and place. But when you do end up with higher probabilities, say focus on your 5-day forecasts, your 40 or 50% probabilities, they tend to verify in the ballpark of 40% of the time. So again, reliable probabilistic forecasts from a global ensemble. Looking at precipitable water, I think we should really focus on the bottom left. I'm not super interested in exceptionally low precipitable water, except for fire weather concerns. I think we're really interested in, can we pick up on a major monsoon surge? And those probabilistic forecasts of exceptionally high precipitable water, again, are fairly reliable at 5, even 7-day lead times, with, of course, a drop-off at 10 days. So I wouldn't be doing my job as a meteorologist if I didn't do a case study. So I want to take a look at a major event that affected Alaska and a good portion of the western U.S. This was a major precipitation, wind, and actually in one case a severe weather event for everything from central Alaska to southeast Utah. And what I really want to highlight here is looking at some of our NAIFS forecasts, what could we pick up on at fairly long lead times? First off, looking at the analysis, you're going to have 500 millbar heights in the top left, 700 millbar temperatures top right, and on the bottom you have 700 wind speed and, again, our integrated water vapor transport, or just bulk moisture transport. So right away you can see we have this significant ridge that's extending in the eastern Gulf of Alaska, exceptionally warm temperatures, small but very low heights in shortwave affecting kind of California into Nevada, very strong winds, especially over southern Alaska, but also extending into a part of kind of Las Vegas into northern Utah. And in the bottom right, very unusual integrated water vapor transport. You've got this big area that's right outside the climatological PDF. So it ended up being a big-time precip event for southern Alaska. So what do we see at 10 days? Now, these are the plots, again, comparing the NAIFS ensemble mean to climatology. And right away, you'll see there's a signal for unusually high 500 millbar heights. I've got these in terms of percentiles. So you're up at the 97th and 99th percentile of heights from an ensemble mean forecast at day 10. And very close to the edge of the climate for 700 millbar temperature. No signal for winds. And this doesn't necessarily mean that none of the members had anything, but there's just not enough agreement. But I think what's really interesting here is that you're already seeing above the 90th percentile of integrated water vapor transport. So there's a signal here 10 days out for an unusual amount of moisture transport. That's something that I don't think we've really picked up on in the past. Looking a little closer, day 7 forecasts, basically the same idea in the top, 500 millbar heights and 700 millbar temperatures standing out quite well there. But you're also just starting to get a signal for some unusually strong winds in the northern Gulf of Alaska and also into the interior. Integrated water vapor transport, you're up close to the 97th and the 99th percentile. So again, a really good signal at day 7 for exceptional moisture transport. Day 5, everything really narrows in here. Now you have, especially in terms of integrated water vapor transport, your ensemble mean is already forecast completely outside the climatology. So this is a case where if you're a forecaster in Anchorage, you're really going to want to be paying attention to this because it's telling you from an ensemble mean forecast, you have something really significant and a lot of potential for heavy rainfall. This is less relevant in the east. We're very interested in integrated water vapor transport in the west because anywhere this coincides with perpendicular orographic barriers, there's a lot of potential for heavy mountain precip. So in the east, you may be a lot more interested in precipitable water. But the message here is that, yes, we can pick up on really strong signals for a significant event at fairly long lead times. Now, the last thing I wanted to point out here, if you look at the 3-day forecast, you really don't have much of a signal for that shortwave that was impacting California and Nevada. So consequently, when the ensemble doesn't have a good handle on that pattern, it doesn't really pick up on the strong winds yet. So you're seeing a clear difference in predictability for these systems of varying scales. So yeah, we got a good handle on the large-scale major event for Alaska, but this fairly potent shortwave trough that affected the Southwest, really not getting a handle on it much until, I would say, 36 hours in this case. And there you're starting to see fairly strong winds jumping right out, as well as some elevated integrated water vapor transport values. So this is a case where a forecaster could really easily be drawn towards these major features in terms of the overall pattern, the temperatures, exceptionally strong winds, and moisture transport. And all of this is easily accessed from the Ensemble situational awareness table. Just showing the analysis, again, we're fairly good forecasts for Alaska and into the Yukon, but we really didn't pick up on that shortwave until very close to the event itself. So the bigger question is, where do we take all of this? And I think the UK Met Office has a great example of how we can translate some of this information into a useful message. What they're doing is they're using what's called an impact matrix. And depending on a combination of confidence going up on the y-axis and impact going across from left to right, it takes a combination of those two to issue their warnings. They only use the word warning, and it's all just color-coded. So they have yellow warnings, orange, and red. And of course, to be able to get to these red warnings of real danger to the public, it takes a combination of confidence and impact. Just the way that it would take a combination of a significant feature and high confidence to produce large anomalies relative to climatology. So this is a case where, yeah, if something really stands out in an ensemble mean relative to climatology or with high probabilities, then you can directly translate that into a message. When I say directly translate ensemble information into a partner public message, I don't necessarily mean automatically, but I think there's a good avenue here to communicate that model information. So concluding here, the smoothing effect of a multi-model ensemble mean can really be used to our advantage. So the mean will only differ significantly from climatology when the bulk of the members from both models agree on the amplitude, the location, and the timing. And when an unusual or extreme event does show up, it's typically a high likelihood that it will verify. And verification has really demonstrated that. So the plus side here is that slam dunks may be more common than we think and may exist at longer lead times than we're used to. And also the probabilistic information that's coming out of the ensemble is fairly reliable in the medium range. And reliability does break down. I didn't cover this too well in the plots, but the ensemble tends to be somewhat overconfident. So a rough take on predictability limits from this ensemble. Again, your mileage here may vary. Looking at major upper-level patterns, pick up on major ridges and troughs 8 to 10 days out, major surface highs and lows getting kind of in the 6 to 8 day ballpark, significant warmth or cold 5 to 7, and really lagging behind everything is moisture. just starting to pick up on significant moisture surges, lead times of 3 to 5 days. Just to make sure I cover the caveats here, not every high-impact event is associated with anomalous upper-level forecast fields. We got to remember that you're not always going to see something that's a really big deal show up in these situational awareness tools. It just says that there are other things that a forecaster will need to look at. Anomalous upper-level fields are not always associated with high-impact weather. Not every high-impact event is well predicted. You may be stuck with a lot of spread in the model and nothing really stands out. And a good example there is the tools kind of struggle with these moderate impact, low confidence events. If you have a lot of spread and something not super significant, it's not going to stand out. But the overall message here is that we're finding Ensemble to be very useful, and I think this is a good situational awareness tool to take advantage of it. So with that, I'll wrap up and take any questions or comments from the group.
Okay, thanks very much, Trevor. So as I was saying earlier, if you have questions, please use the raise your hand feature or use the chat, and we'll convey those. John, do we have any questions? Yes.
Yeah, we have one from Dan Riley. And he was looking at your quad charts and wanted to know if you had a looping capability for those fields.
Yes, actually, if you, I'll just flip back to the table so I can demonstrate this a little bit better. Sorry for jumping through all these slides here.
By the way, I've got Dan off mute, so if you'd like to chime in at any point, feel free.
Yeah, can you hear me?
Yes, we can.
I guess along with that, Trevor showed some nice 4 panels, and a similar question would be, is there a way to, say, customize 4 panels that, might work well for the forecaster?
So a couple of questions there. First one, can you loop these? And yes, by clicking through the table, you can just click on the field you're interested in, and it will open up into all the levels that field's available at. If you click on a level, that will produce a loop on the right that has the forecast for every hour out to 240. So you'll be able to, you can look at a loop of a given field going all the way out to day 10.
Great.
And as far as the 4 panel, I just built that on a PowerPoint slide. So we don't have a functionality where you can look at multiple fields at once in an image, but it's certainly something we can think about.
Yeah, it's really great, great to look at this way.
Okay, thanks, Dan, and thanks, Trevor. Other questions, John, from the audience?
None at this time.
Questions in the room here in Silver Spring? Dennis, you want to get by the mic so they can hear it? We have a question from Dennis Miller here in the room.
Hi, Dennis Miller, OHD. My first question is a simple one. You mentioned ensembles from 2 models at the end of the talk. What were the 2 models?
So we're using the NAICS ensemble, which is a combination of the GEFs and the Canadian ensembles. So 21 members from each system.
What was the first?
It's from the GFS ensemble and the Canadian ensemble.
Okay, 21 members total. Okay.
21 members from each system.
Okay, thank you. And my other question is, do you have plans at this point to make this more widely available? Is this available other than in Western region, or are the people using it?
You can, if you have a NOAA account, you can get to it right now. If that URL, anybody in NOAA can get to that right now. And I think, and he said earlier, Trevor, correct me if I'm wrong, but you're planning to open this up to the public fairly soon, right?
Yeah, there's very little in the way of that. We just have to change a little bit of formatting, and then it'll be completely public.
Do you know if it's being used outside of Western region at this time?
Yeah, definitely. I've heard quite a few comments from people in Eastern region and Central as well. And I should clarify, I have domains available for everything from the WFO scale to all of North America.
Yeah, this is Kathy Gilbert. I was just wanting to follow up a little bit about the connection with the VLab here. So Trevor, what was your vision maybe for working with MDL or somehow getting better support to get this running nationally, or maybe getting it to the point where an individual could tweak it or set their own parameters?
So I don't know if you're going to like this answer, but that wasn't actually my idea.
Okay.
I guess I was asked to share this, but we're pretty happy with the setup we have, where it's available to anyone can get data for their domain. We have it running on a Western Region server. I guess I would need a really good argument to work on making this code completely accessible to people to modify and do anything they wanted with it. It would be a huge effort.
Right. I think we have opened up some discussions about a derivative of this, perhaps being used to support the model blender, but it's just in brainstorming stages at this point. Trevor, I think we're getting a little feedback here, but I'll try to. I question: did you guys? So we had the big anomalous cold winter. What did the tool show with regard to the polar vortex, etc.?
So I don't think I could give you a lot of information there. I could certainly, if you had a particular time you wanted me to look up, I could show you some of the plots. But in general, I mean, it will pick up on exceptionally cold temperatures at fairly long lead times. Just a couple cases I looked at, 7 or 8 days out, you could start to pick up on these really deep troughs affecting the East Coast and very low 850 millibar temperatures. But I don't have any verification specific to polar vortex events. I hate that term, but
well, just so that we're, cold air outbreaks. Oh yeah, I was just curious. Bob, you had a question or a couple?
Yeah, I got a comment and a question. The comment is that using the average or the mean, I think, is being used in lots of places. The regression is based on that, and model blending by various people and so on is doing that. My question is, you're using the word confidence in a lot of places instead of probability, and relative frequencies and standard deviations 2 and 3 and so on and so forth. Is that primarily because you think customers don't understand probabilities or whatever? It seems like there's so many places here where even the departure from climatology could be in terms of probability, in the past, or relative frequency or whatever, and so on, instead of confidence. So what's the main reason for shifting?
It's actually a really good question. And I think confidence is a subjective term that we keep applying when it's really just probabilities. I think confidence is something a forecaster subjectively has when the probability of something is high. And I think we use it in a lot of forecast discussions. We're starting to use it in new products, but I think you're right that a lot of times we'd be better off just saying, here's the probability of something happening. I think that using something like moderate confidence or high confidence, it doesn't always tell you a lot. You'd be better off just saying, look, this is what is likely to happen.
Thank you.
I'll get off my soapbox there. I guess it's a little bit of a philosophical discussion.
No problem. John, do we have other questions on
Let's see. I think in response to your question, Andy Edmond said, Trevor, on the web page, a person can go back to this winter and look at the field. So, I don't know. Is that?
So there's enough of an archive on the web page to be able to look at back in January. How far, or I guess how much data is accessible? How far back can you go?
So the short answer is 7 days, but we have an archive going all the way back to January of 2013. There just isn't enough space on the web server yet to make all that accessible, but it's certainly planned that we'll have everything back to January 1st, 2003, eventually accessible.
Okay. I've got another question. This is Steve Smith in Silver Spring again. You just briefly showed one example of the model climatology approach to this general question, but I'm curious to know if you, at least from a situational standpoint, have developed some, I don't know, rules of thumb or et cetera, where you, I don't know, cross-check the R climate with the M climate or vice versa to help you better understand if it's a real signal or a bogus signal? Or are you just, in other words, how do those two tools work together?
Again, a really good question. We're still figuring out how to use the model climate really well, because the problem is there's a couple of ways you could get a big signal in the model climate. One of them is when you're starting to gain agreement on a really significant event, but the other way is that you have really good agreement on something that's not a big deal in the first place, and either of those could produce the same model climate value. So I think in the best use I've seen of model climate is probably the EFI, which is where you're looking at, okay, how does the whole distribution from the ensemble look compared to the Ensemble model climate. So I think Esril's extreme forecast index that runs on the GEFs is probably a better way to use the model climate, but it's something we're still working on how to apply in operations.
Okay.
One more question.
Sure, go ahead, Bob.
Just curious, where did the terms R climate and M climate come in, creep in? Is that only for this tool, or you said it's been gaining traction?
Those are, I'm not sure how widely those terms are used, but the concept has been applied in a lot of ways. I've seen R climate. R climate would be just any use of comparing model output to climatology. Something even, say, WPC has been doing for ages with their standardized anomalies. But we're trying to create a better interface where you can look at those easily. So R climate has been used a lot, but M climate, I think people are still really experimenting with that.
John, any other questions?
Yes, Israel Jerka, I guess, would like to ask a question.
Yeah, this is SPC. This is Greg Carbon at SPC with a question on the behavior of the anomalies. It was the case you showed the anomaly field. We unmuted?
We can hear you.
Okay, the case you showed, the anomaly appeared to become more extreme as you approach the valid time of the forecast. Have you noticed any behavior when you see run-to-run anomalies perhaps start out relatively large but then decay and you lose that signal, or vice versa? Have you done any work to try to understand how those anomalies behave from run-to-run? And is there anything available that shows run-to-run consistency or inconsistency from the naves?
I don't have an easy way to show that, but at least subjectively from looking at the output for a while, it's unusual for the anomalies to become smaller. And it's mainly because at long lead times, you may have a significant feature, but there's just a lot of disagreement. So what will usually happen is with decreasing model spread, you end up with gradually larger and larger anomalies as the ensemble mean starts to depart further and further from climatology. To go the opposite direction is a little bit unusual.
Thank you.
Other questions, John?
Yes, Steve Knighton would like to know, what does the matrix look like if you get an extreme anomaly in one part of the domain and the opposite extreme in another part of the domain?
In that case, you're going to have to dig in a little further because it's really just going to go with the largest magnitude departure from climatology. So if you had a -4 in one area and a +3 in another area, they're both a big deal, but all it's going to show in the matrix is a -4. In that case, you would want to click your way through and actually look at an image to assess that.
This is Steve Smith again. A question on, so applying these techniques or tools to short-range ensembles, have you looked at that? And in other words, down into the 24-hour or less period, do you think that would be useful at all, or having some sort of transition between this tool and a similar thing in the short range?
I think there's definitely a need for that. The mechanics of it are difficult because when you're looking at large scales, it's easy to just compare a 1 degree ensemble mean forecast to some, say, ½ degree or 1 degree reanalysis. But if you wanted to take something like, say, the SREF CAPE and say, well, is this an unusual amount of CAPE? It really comes down to truth. So how good is whatever reanalysis you're comparing to that? And if you wanted to use, say, the full resolution SREF, if you're comparing a 16-kilometer SREF ensemble forecast to climatology, I think you'd have a hard time coming up with that climatology. But for those, I know someone from SPC is on the phone. You may have another option for that. I don't know if the mesoanalysis has been going long enough that some kind of climatology could be created from that.
SPC, you want to respond to that?
Let me know who that is.
Yeah, Israel, I think.
Oh, okay.
Hang on, we're going to unmute you.
Oh, there we go.
You're unmuted, SPC.
I mean, the only thing analogous would be our surface OA, or what's our from our mesoanalysis page that's created from the formerly RUC, now RAP analysis, where we blend surface observations in and then use the RUC or RAP atmosphere. So that goes back to about 2003. So that would be, type of thing you could use as a climatology, but clearly that's not a very long period.
Okay, thank you. Any other questions?
No.
We're good. All right. Well, I want to thank Trevor very much for presenting this again, and I think it's a great tool. It's good to know that it's going to be made public as well, so you'll start to get some feedback from non-NOAA users. And again, I think we have been discussing internally about the general idea of using this kind of tool or something like it as a pilot for perhaps engaging the SUs in the Model Blender project, and those discussions will continue. So we'll be talking about that offline. I just want to remind folks, coming up in March, we have a talk on the CI flow, Coastal and Inland Flooding Observation and Warning Project. That's being run, I think, out of NSSL. Is that correct, John?
I think so,
yeah. And in April, we're going to have an update from Lance Rothfuse on the facets. And in May, we've got Matt Davis booked to talk about where things stand with IRIS. So I hope you can keep those things in mind. And
which IRIS? IWRSS or
IRIS, yes, not the water one. So again, thanks everyone, and we'll see you again in March. Signing off.